Okay, here we see the generator with a wire and some aluminum strips from which is hanging, in this case, a loop of wire. And of course, one of your experiments deals with, darn it, well, in attempting to set this up, I seem to have dropped my magnets in the floor, miraculously not damaging them, but I've also managed to tear the loop off of the end of the wires. I had this thing nicely set up a minute ago. I'll have to replace everything. Part of the process. Okay, now hang the loop. We're just going to, might as well see how we do this. It's not real complicated. We just crimp the aluminum wire around one, then around the other part of the loop, so that now we have the loop suspended from the aluminum strips. Now, what we're interested in the experiment is the way the loop reacts to the magnetic field of a magnet. But here, we're just going to demonstrate. I lost the loop again. We're going to demonstrate that the current in these wires reacts to a magnetic field. Now, I'm not going to show you the magnet, but there's a magnet just down off of the end of the screen. When I crank the generator, the magnet attracts the wires. Attracted it so well there that it got stuck on the paper. If I crank in the opposite direction, there's a repulsion, but it's a little harder to see that. In any case, this is what happens. Now, if I suspend these so they're not touching paper, if I can get them to cooperate long enough, again, we see the attraction and we see the repulsion. Now, you probably can't tell. See, there's a little bit of attraction. There's repulsion. Hopefully you can tell that they went in opposite directions. So in any case, there's a definite reaction between the current in the aluminum strips and the magnetic field. Now let's take these magnets away so you can't see. Don't want to give away the results of the experiment. It actually looks like we did manage to break two of those magnets. That's aggravating. Okay. Now in class we calculated what would happen in an aluminum strip if we had a certain voltage. Okay? Now, it turns out that we can calculate current from voltage, obviously, if we know the resistance. And we can calculate the resistance of a material by some simple proportionalities. Let's go ahead and cut to the proportionalities. The resistance is a proportionality constant, which we call rho here for resistivity, simply times the length of the conductor divided by the cross-sectional area. Now this applies to a conductor that has a uniform cross-sectional area A and some length L. The longer the conductor is, the more resistance you have. The greater the area, the less resistance you have, because of course greater area means greater volume, means more charge carriers, giving you lesser resistance. Greater length means there's less tendency for the electrons to accelerate, even though there are more electrons available. They don't accelerate as rapidly over a greater length for a given voltage. So this is the proportionality you get. And rho for aluminum we looked up and found to be 2.65 times 10 to the negative 8 ohms times meters. Now this symbol for ohm is just the Greek capital omega, and it stands for ohms, which is the unit of resistance. So that a 1 ohm resistance is 1 volt divided by 1 amp, meaning that if you have a 1 volt potential difference that's giving you a 1 amp current, there's a 1 ohm resistance. Okay, again, I think I said it right, but a 1 volt potential difference that gives you a 1 amp current is a 1 ohm resistance. Now for the aluminum strips that we measured in class, a couple things. We measured several square centimeters of aluminum and divided to find that the density of the aluminum, the density per square centimeter of aluminum foil was 0.007 grams per square centimeter. That implies a thickness of about 0.0027 centimeters. Now, how do we get that? We get that from the density of aluminum, 2.6 grams per square centimeter. That should be per cubic centimeter there. Okay. Now it probably doesn't look like anything at all, but it's supposed to be a cube. Okay. There's 2.6 grams per cubic centimeter of aluminum and 0.007 grams per square centimeter. From that, a little bit of geometry, we easily determine that the thickness is 0.0027 centimeters. The width of the aluminum strip that we measured, somewhat wider than the strips that we just saw, is 2 centimeters. The length is 23 centimeters, and that's about the length of the strips that you just saw. The strips that we measured are considerably wider than the ones that we just saw on the video clip, but the lengths are about the same. Now, the cross-sectional area of the aluminum strip is therefore equal to its width times its thickness. So we can get the cross-sectional area to find the resistance, and we then use the length 23 centimeters here, and we've got all we need to calculate the resistance of the aluminum. And we do that here. Little glitch here. I guess we covered this up without writing it in. Let me see if I can write that in. What we're supposed to have in the denominator here is 5.4 times 10 to the negative 7 square meters, which is the area, which we get by multiplying the thickness by the width. Okay, so let's see if I can write that in. That's 5.4 times 10 to the negative 7th centimeter squared. Probably not very legible. But I think it shows up all right in your class notes. Anyhow, that comes out 0.011 ohms, a little more than 1/100th of an ohm. Okay, so here we've calculated the resistance of a typical aluminum strip. For the aluminum strips that we just saw, the width is more like probably 0.3 centimeters. So we would have a different area and an even, well, we'd have a somewhat higher resistance. The resistance would be about 6 times higher, maybe close to 1/10 of an ohm. But still, there wouldn't be very much resistance.